Hello everyone, myself Indranil Mondal, Assistant Professor in Mechanical Engineering Department. Today I am going to present another important topic, combustion and combustion chambers related to internal combustion engines and automobile engineering. Let's start the session. These are the main contents: introduction, ignition limits, theory of combustion in spark ignition engine and knocking phenomena in spark ignition engine. Let us discuss one by one. Combustion is a chemical reaction in which certain elements of the fuel like hydrogen and carbon combine with oxygen, liberating heat energy and causing an increase in temperature of the gases. The conditions necessary for combustion are the presence of combustible mixture and some means of initiating the process. The theory of combustion is a very complex subject and has been a topic of intensive research for many years. In spite of this, not much knowledge is available concerning the phenomena of combustion. The process of combustion in engines generally takes place either in a homogeneous or a heterogeneous fuel vapor air mixture depending on the type of engine. Let us discuss homogeneous mixture and heterogeneous mixture. Homogeneous mixture. In spark ignition engines, a nearly homogeneous mixture of air and fuel is formed in the carburetor. Homogeneous mixture is thus formed outside the engine cylinder and the combustion is initiated inside the cylinder at a particular instant towards the end of the compression stroke. The flame front spreads over a combustible mixture with a certain velocity. In a homogeneous gas mixture, the fuel and oxygen molecules are more or less uniformly distributed. Once the fuel vapor air mixture is ignited, a flame front appears and rapidly spreads through the mixture. The flame propagation is caused by heat transfer and diffusion of burning fuel molecules from the combustion zone to the adjacent layer of unburned mixture. The flame front is a narrow zone separating the fresh mixture from the combustion products. The velocity with which the flame front moves with respect to the unburned mixture in a direction normal to its surface is called the normal flame velocity. In a homogeneous mixture with an equivalence ratio, that is the ratio of actual fuel air ratio to the stoichiometric fuel air ratio, close to 1.0, the flame speed is normally of the order of 40 cm per second. However, in a spark ignition engine, the maximum flame speed is obtained when equivalence ratio is between 1.1 and 1.2, that is, when the mixture is slightly richer than stoichiometric. Let us discuss heterogeneous mixture. In a heterogeneous gas mixture, the rate of combustion is determined by the velocity of mutual diffusion of fuel vapors and air, and the rate of chemical reaction is of minor importance. Self-ignition or spontaneous ignition of fuel air mixture at the high temperature developed due to higher compression ratios is of primary importance in determining the combustion characteristics. When the mixture is heterogeneous, the combustion can take place in an overall lean mixture since there are always local zones where equivalence ratio varies between 1.0 and 1.2 corresponding to maximum rate of chemical reaction. Ignition starts in this zone and the flame produced helps to burn the fuel in the adjoining zones where the mixture is leaner. Similarly, in the zones where the mixture is rich, the combustion occurs because of the high temperature produced due to combustion initiated in the zones where equivalence is 1.0 and 1.2. In spark ignition engines, carburetor supplies a combustible mixture of petrol and air and spark plug initiates combustion. Combustion is dependent upon the rate of propagation of the flame front. In a spark ignition engine, the maximum flame speed is obtained when equivalence ratio is between 1.1 and 1.2, and for heterogeneous mixture, the combustion takes place in an overall lean mixture where equivalence ratio varies from 1.0 and 1.2. This is all about the basic introduction of combustion process. Ignition limits. Ignition of charge is only possible within certain limits of fuel-air ratio. Ignition limits correspond approximately to those mixture ratios at lean and rich ends of scale, where heat released by spark is no longer sufficient to initiate combustion in neighboring unburned mixture. For hydrocarbons fuel, the stoichiometric fuel-air ratio is 1:15, and hence the fuel-air ratio must be about 1:30 and 1:7. This is the ignition limit for hydrocarbons. This portion is too rich and this portion is too lean. Let us discuss about the various stages of combustion in spark ignition engine. This is the theoretical pressure crank angle diagram. This axis is pressure and this is crank angle. During the process of compression A to B, combustion B to C, and expansion C to D in an ideal 4-stroke spark ignition engine. In an ideal engine, as can be seen from this figure, the entire pressure rise during combustion takes place at constant volume, that is at top dead center. However, in an actual engine, this does not happen. The detailed process of combustion in an spark ignition engine is described by this figure. The pressure variation due to combustion in a practical engine is shown in this figure. There are 3 zones: ignition lag, propagation of flame, and after burning. Capital A is the point of passage of spark, say 20 degrees before top dead center. B is the point at which the beginning of pressure rise can be detected, say 8 degrees before top dead center. And C, the attainment of peak pressure. Thus, AB represents the first stage, BC represents the second stage, and CD represents the third stage. The first stage, A to B, is referred to as the ignition lag or propagation phase, in which growth and development of a self-propagating nucleus of flame takes place. This is a chemical process depending upon both temperature and pressure, the nature of the fuel, and the proportion of the exhaust residual gas. Further, it also depends upon the relationship between the temperature and the rate of reaction. The second stage, B to C, is a physical one, and it is concerned with the spread of the flame throughout the combustion chamber. The starting point of the second stage is where the first measurable rise of pressure is seen on the indicator diagram. That is the point where the line of combustion differs from the compression line, that is point B. This can be seen from the deviation from the motoring curve. During the second stage, the flame propagates practically at a constant velocity. Heat transfer to the cylinder wall is low because only a small part of the burning mixture comes in contact with the cylinder wall during this period. The rate of heat release depends largely on the turbulence intensity and also on the reaction rate, which is independent on the mixture composition. The rate of pressure rise is proportional to the rate of heat release because during this stage the combustion chamber volume remains practically constant. The starting point of the third stage is usually taken as the instant at which the maximum pressure is reached on the indicator diagram, that is point C. The flame velocity decreases during this stage. The rate of combustion becomes low due to lower flame velocity and reduced flame front surface. Since the expansion stroke starts before this stage of combustion with the piston moving away from the top dead center, there can be no pressure rise during this stage. So this is all about the various stages of combustion in SI engines: ignition lag stage, flame propagation stage, and after burning stage. I have already told these points: ignition lag stage, flame propagation stage, and after burning stage. Now let us discuss what are the main factors that influence the flame speed. There are so many factors: turbulence, fuel air ratio, temperature and pressure, compression ratio, engine output, engine speed, and engine size. Turbulence. The flame speed is quite low in non-turbulent mixers and increases with increasing turbulence. This is mainly due to the additional physical intermingling of the burning and unburned particles at the flame front, which expedites reaction by increasing the rate of contact. The turbulence in the incoming mixer is generated during the admission of fuel air mixture through comparatively narrow sections of the intake pipe, valve openings, etc. in the suction stroke. Turbulence, which is supposed to consist of many minute swells, appears to increase the rate of reaction and produce a higher flame speed than that made up of larger and fewer swells. A suitable design of the combustion chamber, which involves the geometry of cylinder head and piston crown, increases the turbulence during the compression stroke. Generally, turbulence increases the heat flow to the cylinder wall. It also accelerates the chemical reaction by intimate mixing of fuel and oxygen so that spark advance may be reduced. This helps in burning lean mixers also. The increase of flame speed due to turbulence reduces the combustion duration and hence minimizes the tendency of abnormal combustion. However, excessive turbulence may extinguish the flame, resulting in rough and noisy operation of the engine. Fuel air ratio. The fuel air ratio has a very significant influence on the flame speed. The highest flame velocities, that is minimum time for complete combustion, are obtained with somewhat richer mixture, which shows the effect of mixture strength on the rate of burning as indicated by the time taken for complete burning in a given engine. Temperature and pressure. Flame speed increases with an increase in intake temperature and pressure. A higher initial pressure and temperature may help to form a better homogeneous air vapor mixture, which helps in increasing the flame speed. This is possible because of an overall increase in the density of the charge. Compression ratio. A higher compression ratio increases the pressure and temperature of the working mixture, which reduce the initial preparation phase of combustion and hence less ignition advance is needed. High pressures and temperatures of the compressed mixture also speed up the second phase of combustion. Increased compression ratio reduces the clearance volume and therefore increases the density of the cylinder gases during burning. This increases the peak pressure and temperature and the total combustion duration is reduced. Thus, engines having higher compression ratios have higher flame speeds. Engine output. The cycle pressure increases when the engine output is increased. With the increased throttle opening, the cylinder gets filled to a higher density. This results in increased flame speed. When the output is decreased by throttling, the initial and final compression pressures decrease and the dilution of the working mixture increases. The smooth development of self-propagating nucleus of flame becomes unsteady and difficult. The main disadvantages of spark ignition engines are the poor combustion at low speeds and the necessity of mixture enrichment, that is equivalence ratio between 1.2 to 1.3, which causes wastage of fuel and discharge of unburned hydrocarbon and the products of incomplete combustion like carbon monoxide, etc. in the atmosphere. Engine speed. The flame speed increases almost linearly with engine speed, since the increase in engine speed increases the turbulence inside the cylinder. The time required for the flame to traverse the combustion space would be halved if the engine speed is doubled. Double the engine speed and hence half the original time would give the same number of crank degrees for flame propagation. The crank angle required for the flame propagation during the entire phase of combustion will remain nearly constant at all speeds. Engine speed. Next, discuss engine size. The size of the engine does not have much effect on the rate of flame propagation. In large engines, the time required for complete combustion is more because the flame has to travel a longer distance. This requires increased crank angle duration during the combustion. This is one of the reasons why large sized engines are designed to operate at low speeds. These are the main factors that influence the flame speed: turbulence, fuel air ratio, temperature and pressure, compression ratio, engine output, engine speed and engine size. Next, discuss illustration of various combustion rates. This figure illustrates various combustion rates. The rate of pressure rise in an engine combustion chamber exerts a considerable influence on the peak pressure developed, the power produced and the smoothness with which the forces are transmitted to the piston. The rate of pressure rise is mainly dependent upon the mass rate of combustion of mixture in the cylinder. The relationship between the pressure and the crank angle for three different combustion rates is shown in this figure. Curve 1 is for a high, curve 2 for the normal and curve 3 for a low rate of combustion. It is clear from these figures that with lower rate of combustion, longer time is required for the completion of combustion, which necessitates the initiation of burning at an early point on the compression stroke. Also, it may be noted that higher rate of combustion results in higher rate of pressure rise, producing higher peak pressures at a point closer to top dead center. This generally is desirable feature because higher peak pressures closer to top dead center produce a greater force acting through a large part of the power stroke and hence increase the power output of the engine. The higher rate of pressure rise causes rough running of the engine because of vibrations produced in the crankshaft rotation. It also tends to promote an undesirable occurrence known as knocking. This is all about rate of pressure rise. A compromise between these opposing factors is accomplished by designing and operating the engine in such a manner that approximately one half of the maximum pressure is reached by the time the piston reaches top dead center. This results in the peak pressure being reasonably close to the beginning of the power stroke, yet maintaining smooth engine operation. I have already told this slide earlier. Now let us discuss abnormal combustion. In normal combustion, the flame initiated by the spark travels across the combustion chamber in a fairly uniform manner. Under certain operating conditions, the combustion deviates from its normal course, leading to loss of performance and possible damage to the engine. This type of combustion may be termed as an abnormal combustion or knocking combustion. The consequences of this abnormal combustion process are the loss of power, recurring pre-ignition and mechanical damage to the engine. Phenomena of knock in spark ignition engines. Let us discuss. In a spark ignition engine, combustion which is initiated between the spark plug electrodes spreads across the combustible mixture. A definite flame front which separates the fresh mixture from the products of combustion travels from the spark plug to the other end of the combustion chamber. Heat release due to combustion increases the temperature and consequently the pressure of the burned part of the mixture above those of the unburned mixture. In order to effect pressure equalization, the burned part of the mixture will expand and compress the unburned mixture adiabatically, thereby increasing its pressure and temperature. This process continues as the flame front advances through the mixture and the temperature and pressure of the unburned mixture are increased further. If the temperature of the unburned mixture exceeds the self-ignition temperature of the fuel and remains at or above the temperature during the period of pre-flame reactions, that is ignition lag, spontaneous ignition or auto-ignition occurs at various pinpoint locations. This phenomena is called knocking. The process of autoignition leads towards engine knock. The phenomena of knock is explained by the figure A, which shows the cross-section of the combustion chamber with flame advancing from the spark plug location A without knock, whereas in this figure C, it shows the combustion process with knock. In the normal combustion, the flame travels across the combustion chamber from A towards D. The advancing flame front compresses the end charge B'(D) farthest from the spark plug, thus raising its temperature. The temperature is also increased due to heat transfer from the hot advancing flame front. Also, some pre-flame oxidation may take place in the end charge, leading to further increase in temperature. In spite of these factors, if the temperature of the end charge had not reached its self-ignition temperature, the charge would not auto-ignite and the flame will advance further and consume the charge B'(D). This is the normal combustion process, which is illustrated by means of the pressure time diagram, this diagram. However, if the end charge B'(D) reaches its autoignition temperature and remains for some length of time equal to the time of pre-flame reactions, the charge will autoignite, leading to knocking combustion. From figure C, it is assumed that when flame has reached the position BB', the charge ahead of it has reached critical autoignition temperature. During the pre-flame reaction period, if the flame front could move from B'(B' to only C', when the charge ahead of C' would autoignite. Because of the autoignition, another flame front starts traveling in the opposite direction to the main flame front. When the two flame fronts collide, a severe pressure pulse is generated. The gas in the chamber is subjected to compression and rarefaction along the pressure pulse until pressure equilibrium is restored. This disturbance can force the walls of the combustion chambers to vibrate at the same frequency as the gas. Gas vibration frequency in automobile engines is of order of 5000 CPS. The pressure time trace of such a situation is shown in figure d. It is to be noted that the onset of knocking is very much dependent on the properties of fuel. It is clear from this description that if the unburnt charge does not reach its autoignition temperature, there will be no knocking. Further, if the initial phase, that is ignition lag period, is no longer than the time required for the flame front to burn through the unburnt charge, there will be no knocking. But if the critical temperature is reached and maintained, and the ignition lag is shorter than the time it takes for the flame front to burn through the unburnt charge, then the end charge will detonate. Hence, in order to avoid or inhibit detonation, a high autoignition temperature and a long ignition lag are the desirable qualities for spark ignition fuels. In summary, when autoignition occurs, two different types of vibration may be produced. In one case, a large amount of mixture may autoignite, giving rise to a very rapid increase in pressure throughout the combustion chamber, and there will be a direct blow on the engine structure. The human ear can detect the resulting thudding sound and consequent noise from free vibrations of the engine parts. In the other case, large pressure differences may exist in the combustion chamber, and the resulting gas vibrations can force the walls of the chamber to vibrate at the same frequency as the gas. An audible sound may be evident. The impact of knock on the engine components and structure can cause engine failure. And in addition, the noise from engine vibration is always objectionable. The pressure differences in the combustion chamber cause the gas to vibrate and scrap the chamber walls, causing increased loss of heat to the coolant. The pressure or absence of knocking combustion in engines is often judged from a distinctly audible sound. A scientific method to detect the phenomena of knocking is to use a pressure transducer. The output of this transducer is connected usually to a cathode ray oscilloscope. Typical pressure time traces which can be obtained from a pressure transducer are given in this figure for a normal combustion and from figure small d for knocking combustion. These are all about knocking in spark ignition engines. Whatever I have told, this slide illustrates this phenomena. Normal combustion, I have already told you. Abnormal combustion, that I have told few minutes ago. If you want to get more videos, please like, share and subscribe my channel. Thank you.